that time. Dave actually has down here, he's got that B5. He doesn't actually say it in the back there. He's got, but we would still be accepting that within the next week type of thing. So we will mark that. So if I do the quiz next week, I'd probably get it marked. I'd have it back on that Friday. I'd have it in the office. I'll send you an email that says it's there in the office. So by the Friday, and then that way it'll also tell you when you can redeem until. I believe so, yeah, because that's Dave who will take those on. Yep. So this is on page 124. On page 124, I need to go back and do a typo, I guess, a typo of sorts. Now this is my book, and when I actually do, I actually have my answers sort of prepped in my own book. However, when I did it on the slide, and nobody was awake that day, you know, so it's been noticed by Daniel, which is good that someone's watching it. So I went through the actual slides and noticed that when I went to do the graph in the middle, okay, this was a graph very similar to a sine curve, and I was pointing out that this is where it makes it stationary, so I put a dot there. This is where it's stationary, so I put a dot there. All right. However, my graph on the slide went in the other direction, so it wasn't meant to. It's meant to look like this. Okay. So can you check on page 124? All right, because the velocity, you can tell that the derivative is positive here, so the velocity should have been on the top of the x-axis or the t-axis, should have been negative down there, and it should have been positive. So I had that drawn in mind, but that's not what I got you to draw. So can you fix that up on page 124? And then that would agree my top one, which was interesting, Daniel. My top one agreed, like, because this one here is stationary here, so it was meant to be 0 there. This was stationary here, and then this was stationary here, and this was negative. All of these were coming down, so the top one was correct on the slides. All right, it's the middle one that I didn't do correctly. Okay, is everybody okay with that? Fix that up on page 124. We all right with that? Page 124, righto. So fix that up. And then we are back to this one. This one is the second round of probability. Second round of probability. Now you might need your calculator out. There's a couple of new buttons, all right, for us to explore if you haven't ever come across this. All right, so here we go. We are starting. So basically there is a lot of describing at the beginning, but we've already gone into probability. And what this round is, it's about asking you to do some counting procedures where it's not as obvious, okay? So you've gone past simple probability. This is now going into the, what happens when there's quite a lot of outcomes? Do I always want to draw a tree? And the answer is probably going to be no. So we're going past the obvious. Last week was round one and it was simple. Now we've got bigger sample space. When calculating probabilities, the number of favourable outcomes in the event and the total number of outcomes have to be counted. So this is what happens. The multiplication principle states that if one operation A can be performed in M ways and a second operation B can be performed in N ways, then the two successive operations A and B can be performed in, and you do a multiplication. Now this is on your page 162. All right, so it's saying if you can do this event A followed by this event B, and you then do the multiplication with the number of ways. Now, we don't tend to get you to list it because now you're talking about a lot of outcomes. So we just want you to count them, tell us a total number. So, for example, the question that's already been done for you there says, if I have 3 shirts and 4 trousers to choose from, how many different outfits of a shirt and a pair of trousers do I have? So he's giving you a display here, but you don't really need it, but this is just to help anybody visualise it. You've got shirt A, B and C, and then you've got trousers 1, 2, 3 and 4, and each of these shirts can branch off. So you can see that each shirt has 4 options, and then altogether it's got 12. Now you don't need to do the tree diagram, so this is us saying that's how you might want to visualise it, but they're going to be far too big. All you want to do is be able to count them. So you could do the shirts, okay, 3 ways, and you could do the trousers, all right, in 4 ways. So you just need to multiply 3 by 4. Another example totally sort of done out for you there is about the Emma decides to order an entree, a main and a dessert from the menu at this restaurant. From the menu options given below, how many different 3-course meals? So you've just got to be careful. They want a 3-course meal which involves an entree, a main and a dessert. Now they're not going to want you to list it. They just want to know how many different ways can you do it. Entree there were 2 ways, mains there were 3, desserts there were 2. So there are actually 12 ways. For anyone that wants to visualise it, there's the actual tree diagram. And again, you won't be getting to do that, but again, it's just helping some people get past the, oh, this is how I can see that there are 12 actual outcomes in it. So down the bottom, it says the addition principle states that if one operation A can be performed in M ways, and a second, and these words mutually exclusive pop up, operation B can be performed in N ways, then it says then the 2 operations A or B can be performed in, and you'll notice that it's now got a plus there. So if you want to highlight that compared to the first one, still on page 162, still on page 162. Now you're adding the number of ways A can happen or the number of ways B can happen. So you're adding those answers. So he's given you a graphic on the apples, the bananas and the oranges. All right, and he's trying to say that these apples are different. So you'll notice he's given us 3 different apples. He's given us 3 different bananas and he's given us 2 oranges. And it says how many different combinations of 2 different pieces of fruit. 2 different pieces of fruit. And again, you're being asked, you could have an apple and a banana, or an apple and an orange, or a banana and an orange. So you're going to be noticing that this says ors, so there's about to be some additions popping up. So how can you do the apple and the banana? Well, there's 3 ways of picking the apple, 4 ways of picking a banana, so obviously you just go through 12 ways of coming up with an apple-banana combo, 6 ways of coming up with the apple-orange combo, and there's 8 ways of coming up with a banana-orange combo. So altogether there are 26 different 2-piece combinations there. 26. Now you don't have to list them. So these are where you're now getting past the give up on the listing, but it's a good idea to write something down like that to help you start the solution. So writing something down like that doesn't mean I've written everything down, not all the outcomes. I've just said this is what I need to investigate, and then I've broken it into smaller problems. So here's what happens next. Up on the next page, the thing you want to be careful of is when you're reading these questions, you want to note all the small details. So, for example, it says repetition allowed. 4-digit PIN numbers are formed from the digits. You're only using a 6, a 7, an 8 and a 9, and all numbers may be repeated. Okay? How many different PIN numbers are possible? Now most of us will either draw little boxes or we might just draw some dashes to say, well, the pin's got to have 4 numbers and I've got to fill in, okay, how many ways can I pick a number for the first position, and that would be 4. Now that number goes back into the draw because you're allowed to repeat it. So there's 4 ways to pick the second number, 4 ways to pick the third number, and 4 ways to pick the 4th number. So altogether, you have got a multiplication. You've got 256 different pins that could come out of using a 6, a 7, an 8 and a 9. So 256. Now that's important because they're going to ask you the probability of something happening. And if you don't know how to count the possible outcomes, then you don't know how to do your probability questions for this particular lecture. So finding out how to count, all right? Second one says the repetition is not allowed. So you should hear in the clue somebody saying something has not been replaced, or in this question it says no number can be repeated. So that straight away changes the program because you've got, again, 4 boxes or 4 dashes. To start off with, you've got the 6, the 7, the 8 and the 9, so there are 4 things you could pick. But once you've picked one of the numbers, it's now out of selection. So there are 3 left for the next one. 2 numbers have been put down, you've only got 2 left. 3 numbers have been put down, you've only got 1 left. And how many ways can this happen? So now you've got 24. You've got 24 pins that can be formed using a 6, a 7, an 8 and a 9 if no number has been repeated. Okay? So again, crucial that you pay attention to those details. This one here, people tend to find hard, this little idea. If any one of k different mutually exclusive events can occur on each of these n trials. So my first thought is this is the bit that people should lock in. You are doing an experiment over and over and over again. So the n trials is how many times you do it. Now sometimes people don't know where to find that clue. If you're picking 8 students, let's say, then you're doing it 8 times, all right? If you're rolling the dice 5 times, then you're doing the experiment 5 times, all right? So it's that's important because that's the number that goes up high. Now a lot of people get that there's a k to the n. They know there's a number to a power, but they mix the numbers up in the positions. So n is the number of times you repeat the experiment, if you want to say it that way. And k is how many things could happen. All right? How many things could happen? So it says, to get your mind thinking, you've got a coin. What happens with a coin? Well, there's only 2 things that can happen. It's a head or a tail. So that means that the k is equal to 2. So if you want to sort of just jot that down. I know the answer's there, but you're asking yourself, what could happen? 2 things could happen. So it's 2 to the power of, and it's how many times did you repeat the experiment? And the answer to that is I did the experiment 8 times. So something like that that makes you get the numbers in the right places. I've got a die, so 1 die being rolled 3 times. This sounds like my n is 3, but what's the bottom number? Now the base number, the k, is how many outcomes are there when you roll a die. Okay, a die has 6 outcomes, so k is equal to 6. A 1, 2, 3, 4, 5, or a 6. So it's got 6 possible outcomes, so it's 6 to the power of 3. So there are 216 outcomes. Nobody will get you to list them, okay? They just want you to figure out how many, all right? So how many times. Now then it comes over to us. We've got this license plate question, so this is for us to fill in. If a license plate consists of 3 letters followed by 3 digits, so again, listening to the clues, it sounds simple enough. How many unique number plates are possible? Okay, so what we'll do, I just gave myself a bit of space, know where I am. 3, 4, 5, 6. What I tend to do is I tend to remind myself that these ones here are going to be letters and these ones here are going to be digits. So in some way, make sure you see the rules to this number plate. Now, we've had a discussion in everybody's group when we do this. How many letters are in the alphabet? You'll be amazed that people don't know the answer. So make sure you do, all right? There are 26. So you go to put 26 in. Now, here's the other problem. People put more words onto their piece of paper. So sometimes people go, oh, okay, does that mean it'll go 25, 24? Now, you've seen more words than I've written on my page, because on my page here, it does not say anything about things can't be repeated. So stop putting extra words into your questions. It doesn't say anything about it. So that means the 26 are back for the second, the 26 letters are back for the third. That means you could get an AAA, all right? It means you could get a ZZZ, all right? Followed by 3 digits, all right? How many digits have we got to pick from? Hopefully we've got 10, all right? You've got the 9 plus the 0, so there's going to be 10 times 10 times 10. Now, if these boxes or these dashes here, they help me out, they plan it, these are going to be used from now on. When you see me do my answers, you'll see this. It helps me set up what I'm looking for. And the final answer, you can push that in, whatever that becomes. It's a big number. So call it out when you're ready, if you've got it. Too big for you to say. What kind of a mathematician are you? So we've got 17 million. So 17 million, 576, 576,000. Now we're not going to get you to label them all, but at least you know how many unique number plates there are. Because again, what's the probability of me having, just think of mine, I have a standard old number plate, just like one of these. I have one of those old yellow ones. All right, what's the probability that you have mine, right? That you can find mine would be 1 out of 17,576,000. So mine is just one of those ordinary ones. So it says on the next one, what if the number plate begins with the letters B, M, C? Now these are called restrictions, and what you want to learn to do is if a question has placed restrictions, then you apply those restrictions first. So the B has to be here, there's one way that happens. The M has to be here, there's one way that happens. The C has to be here, so there's one way that happens. It has to be in that order. Starting with, it says begins with the letters, and it has to be BMC. So sometimes there are companies that have that on their number plates. So you see BMC might stand for some company, and then they run the numbers off it. Now it says nothing else, it just says how many different number plates are possible. So then that means there's 10 digits, 10 digits, and 10 digits. So out of that 17,576,000, how many of them have a BMC followed by a number? 1,000 of them. So this company, for example, could have 1,000 of these vehicles until it would then have to figure out what else to do for its employees. All right. If the number plate starts, what's he done there? If the number plate starts with, let's get rid of that typo. If the number plate starts with A and ends with 7, how many different number plates are possible? Again, the ruling is always apply your restrictions. It has to start with an A and it wants to end with a 7, so there's one way that happens. Now remember, this is still 3 letters followed by 3 digits. So it's again, this is a letter with a letter, this is a digit with a digit. Now don't multiply by the 7, that is actually A7, all right, and A. So figure out what that'll give us. 67,000. Anyone else? 67,600. Again, that is how many out of the 17,576,000 would start with an A and end with a 7. Again, if you were finding the probability, I'm starting to have you think, if you were asked to find the probability that it starts with an A and ends with a 7, it would be this number over the total number. That's how you start thinking about your probability questions that are coming today. Now these two words get thrown at us, a permutation and a combination. And as easy as can be put, a permutation is an ordered selection and a combination is an unordered selection. Now most people can repeat that to me. They know that. What they find hard is reading a question and deciding for themselves, is this ordered or not ordered? Because everybody knows the tools. They say, I know I'll use the P when it's ordered, I know I'll use the C when it's unordered. But it's getting used to the questions and asking yourself every time. So here's what we've got. Explained with a bit of detail on the bottom of page 163. Choose 3 of the letters from an A, a B and a C. So these are the things you could get. Okay, so turned around in all the orders. They are the permutations. That's a permutation is if order mattered. So an ABC is looked at as different to an ACB, which is different to a BAC, which is different to the others. So there are 6 permutations. But if you didn't care about their order, then there's only one way that it comes to you. So an A and a B and a C, if order matters, there are 6 arrangements. If the order doesn't matter, then there's only one arrangement. Okay, so that's where it's going to start getting people's brains overheated usually. Choose 2 of the letters, all right, from the A, the B and the C. Same idea for the permutations. If order matters, all right, you've got those 6 there. For the combination, you've only got 3 because an AB is the same as a BA. So that's why there's less of those. A combination is always a lower number than its permutation partner, I guess, if you want to think of it like that. All right, so it's got a permutation is ordered. Think of P for position. So there's another little link. Think of P for position. And this is worked on the page 164. It's got 6 friends sit in the front row at the theatre. Now most people don't start thinking, but I want you to start thinking about as soon as people sit in a row, that means there's order involved. So when people sit in a row, when people stand in a queue, any of those sort of things are implying that there's order. Okay, so you want to start thinking about how am I going to see when the questions come my way. Once you see order, then most people will say it's a P that I'll be using, a permutation. How many possible seating arrangements are there? So what ends up happening, again, you can do this with the boxes, which is handy. There are 6 ways that they can fill the first position, but once somebody sits down, that person's now out of the mix. So there are 5 ways the next seat can be taken. 2 people are sitting down, so there's 4 ways, and then 3, and then 2, and then 1. Now all those numbers are going to get multiplied together, and there's a shortcut way of doing that, all right? So it's going to be popping up soon. It says when objects are arranged in order, each possible arrangement is called a permutation, and that particular 6 by 5 by 4 by 3 by 2 by 1, it's got to reach 1 for it to be called. Do you know what the word is? Anyone seen it before? A factorial, okay? So what happens is the number of ways that all those n objects can be arranged in order, it starts at n and it goes down by 1, down, 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 but it has to get all the way to the bottom, and it's called a factorial. And there is a button on our calculator for factorial, okay? So I'll put the visualizer on for a second. On most of these, it's up in the right-hand corner. So most of these, it's up in the right-hand corner. Everybody's got one. And it saves you time rather than pushing 6 by 5 by 4 by 1 and all of that. So here's the button that I'm talking about. Up on this one, it's that one there. So it's got an exclamation mark. So if you want to put a 5 with a factorial, it will do it for you, so you don't have to push as much. Gives you 120. We had 6 factorial. So make it a 6 factorial. 720. Now even the older ones will have it. So has everyone found their own button? So make sure you put a note on that page, right there on page 164, and say there's a calculator button for you to investigate called factorial. Righto? So back over to this one here. So this factorial question, all right? Now remember, that's if it goes all the way down. So that's going to pop up again in a little while. It says if 5 different books are to be arranged on a shelf. Again, you're arranging books on a shelf. Now, you don't hear the word in order. You've got to assume that books being put on a shelf, all right, seems to imply that there will be order. So what you put in the shelf first, then what follows, then what follows. Again, it's like sitting down in a front row. So when you've got order, you know this is going to be some sort of a permutation. And again, 5 books, it says 5 factorial, okay? Now it's got some people. How many ways can Amy, Billy, Chris and Dan be arranged in a line? So again, what you want to do is just be able to, that's just so I can see how far I can write down there. There are 1, 2, 3, 4, so I've got 4 positions ready to go. And it says how can I fill those? Okay, arranged in a line. Again, because they're being arranged in a line, I will write the word order. So that means that the position is important. So there's 4 of them that can take the first position. Then I'm left with 3, then 2, then 1. This is otherwise known as 4 factorial. All right, so whatever 4 factorial ends up being. There are 24 ways this can happen. Okay, 24 ways that these 4 people can sit down. Now the very next thing I want you to highlight, but, well, I want you to highlight it because it asks you in how many ways can Amy, Billy, Chris and Dan be arranged in a circle. Now this is just of interest. It is not tested. So put of interest, not tested, not examined. All right, because it just wants you to think as a bit of a challenge. Once you put a circle position, like a circle table, a round table situation, all right, what ends up happening is you place the first person, all right, and then it's not so much that, it's the other 4 people, sorry, the other 3 people that you are arranging. So we've got, in this case, I'll just put here n was 4, so we did a 4 factorial. In this case, n is 4, but, I'll just put here, but it's not 4 factorial when you're around a circle, all right, it actually goes down by 1. So you can place the first person and then you go and have a look at where the other 3 are sitting. So it actually comes up as n minus 1 factorial when it's in a circle. Now that's of interest, it doesn't get examined. So this would have been 3 factorial, and a 3 factorial turns out to be a 6. There are 6 ways you can place these people in a circle or round a table. That's a round one. So just make sure you highlight that. That's on page 164, all right? You might have come across it in your school maths if you did that, but we don't examine it here. Now, probably what happens to us mostly, though, is it says in many instances we need to know the number of ways that a subset of that group of objects can be arranged. So just then we arranged 5 books, so it was 5 factorial. We had 4 friends, it was 4 factorial, because they're all being placed. But usually we don't place the whole lot, we have a subset of that group being placed. So here is when you get this NPR. Now this is its formal definition. It says n factorial over n minus r factorial. However, we know that there's a button on our calculator. Now you might have studied this in maths again. Back at school you might have had been in the course, and you know that you had to remember that definition. In this particular one, it's of interest, it's there, but you know you're going to use your calculator to find the NPR, all right? And what it stands for is that you can make, from selecting from R objects from a total of N. Now I'll say these words, the N, which is the one up high, is the bigger number. It can be the same as R, but R will never be bigger. So say, for example, this number was a 6. Let's make it a 7, sorry. Say it was a 7 up high. R can be any number up to 7, and it can be including 7. It just can't be more than 7, all right? So it will never be bigger than N. N is the total that you would have. So here's what we've got. In how many permutations can I select 2 items from 5? Okay. So this one, has he got it worked there? He got that worked. Oh, up the top of page 165. He's got that there. So he's only got 2 positions to fill, but he had 5 items to pick from. So what ends up happening is that there's 5 by 4. You'll notice this is not the time to use factorial, because this doesn't run all the way down. So you don't see times 3, times 2, times 1. So I'll just put a little reminder here. This is up the top of your page 165. Do not use factorial. Do not use factorial here, because it's not running all the way down. So just don't get caught in that. So because it's got a 5 by 4, which is 20 ways, all right, the other way of doing that, that's the formal way, but we also know that there's a button. So you might start looking at your calculator. Maybe you've used it before. We want 5p, and we're doing a subset of 2. Now, Dave's put the actual definition way there, but we won't be using that because it does consume up time. So on your calculator, do you all know where your P button is? So I'll just flip over to that for a moment. Everyone's got one. Ours happen to be on the multiplication and the division. Okay, ours are on the multiplication and the division, but you've got to use your shift. So just get used to seeing how it will appear on your screen. So I wanted a 5, then I wanted the P, and then I wanted the 2. So that's what it looks like on my screen. Everyone check your own calculator on what it looks like. The answer to that should have been 20, which it is. That's you saying, for example, I've got 5 people, but I've only got 2 seats to fill. All right? That's what you are talking about. So you won't need to go through this other way. All right, I'll flip back over. You won't need to go through all of this. You know that you can go straight to the calculator with that one there, as long as you know where it is. You don't have to, by the way. If you've got the 5 times the 4, that gives you the answer anyway. You don't have to go and push it in with a P. It gets you the same answer, okay? So he's just pushing in that 5p2, so everyone's found it. And it says this means that there are 20 permutations, which means different arrangements that can be made when selecting 2 items, which is a subset from the 5 different items, okay? So then it says this was from before, that earlier one where you had the 3 letters and you wanted to only pick 2. So in fact we could have done that straight out by putting 3, because there were 3 letters to pick from, and then we wanted the subset of 2. So that's why the subset of 2 is there. So 3p2 would have given us our 6 as well. Now we've got some questions on page 165. The main thing is what I do here is ask myself, is it ordered or not? Okay. Now some of the questions will come out with a word and some won't, so you want to be able to stress to yourself, if there is room for only 3 books on a shelf, in how many ways can 3 books out of a possible 5, so I've got 5 on the bench waiting to be put up there, if they are arranged in order. Now when you put books up on a shelf, I don't think you have to expect them to say arranged in order, because the last question that we had books just said how many ways can it be done. Books being put up on a shelf just imply order, okay? So because it's got the word order, you know that it's going to be a P, so I tend to put that down. How many did I have? So the N was 5, so it's going to sit high. My subset, all right, I'm going to get only 3 books onto the shelf, so my R is 3. So that's why it sits down there. So just a 5p3, so a 5p3 ends up being a 60. Again, you can also go with that and say, well, there were 5 ways, by 4 ways, by 3 ways, and that came to a stop. All right, so it would give you the same answer. It would still give you 60. So what we've got popping up after that is the next one. We've got, there are 10 competitors in a race. In how many ways can the first 3 places be filled? We tend to make questions that have places, first 3 places, gold medal, anything like that, silver and bronze. These are implying that there's order, so order implies that there's a P. How many did you have to pick from? There were 10, so N is 10, so I've got my P, I've got my 10, and then I'm taking subsets of 3. So here is the subset right there, R is equal to 3. So you're going to put your 10p3 in. 10p3 ends up being 720. Now you could also do it with those 3 positions, 10 times 9 times 8, same answer. Alright, so it doesn't matter which way you go with it. Alright, there's one more, just to get used to some of our questions. It says you're going to be electing a president and a vice president. As soon as you hear that there's some sort of rank involved, someone's a captain and a vice captain, someone's a secretary, someone's a treasury officer, these imply, once you get some sort of label like that, these imply order. So again, it's about finding the question. I know everybody can read the question, but it's about digging down and saying, is that order or not? So I've got 10 people, so it's going to be a 10p, and I'm only filling a subset of 2, a president and a vice president. So if you need to put that on top, there is your R and there is your N, because that's how many people you've got to pick from. You can do it the other way as well, all right? So any way you like, that gets you there. Right over the page, combinations. This is the other family. So now we're expecting unordered. We expect lower numbers than permutations because order doesn't matter anymore. So it says, again, there's going to be a new button to push. It says this NCR is the number of combinations we can make when selecting R objects, that's a subset, from a total of N. So this again happens, a total of N is the bigger number, all right? So here's what we've got. Everybody found it on theirs. We'll just push a 7C4. And again, most people will have it next to the one they were just using. Ours is on the division. So again, I'll zoom in, I'll push 7C, and then we're practicing with a 4. Yeah. I'm just getting that light right in there. Trying to see where that is. So if you've got that calculator, what you want to do is push your 7. Because you need that, it's in that, whatever colour you call it, yellowy, orangey colour, you need a shift to bring the C up onto your screen, and then you need the 4. So you've got to make sure you get the C onto that screen. Should give you a 35. Should give you a 35 there. Alright? Push that in, check it out, tell yourself there is a calculator button. Again, that's not the hard part. The hard part is deciding when is it, okay, going to be a combination. So again, we're going to go through. It's saying this means that there are 35 combinations which are unordered selections that can be made when selecting 4 items from 7. Just compare it to 7p4. Now I'll tell you it's going to be a bigger number. So 7p4. So have a look at the difference. Anyone else get 840? So you can see that if you make a mistake, you will get, all right, you'll get yourself 840. If by accident, that's going to be the problem. When all the questions are mixed up, how will I know to pick the P? How will I know to pick the C? The answers are very different. So this is saying there is no order involved. So we've got to get used to some of these questions. This was the one from before. We said that if order was involved, we would have used 3p2 and got 6. Let's see if it works for this one. A 3c2 gives you an actual number of 3. And that was what we had decided before. When order doesn't matter, an AB is the same as a BA, and so on. So there were less of them. So we are down on the bottom of page 166. Now this has been sort of written out for you. You can see all of those permutations, all of the teams. So 6 friends plan to play tennis. How many different teams of 2 players are possible? So doubles teams. Okay. So I've got 6 to pick, and when I pick a team that has Nicholas and Rebecca is the same as a Rebecca and a Nicholas. So they're not 2 different teams, they are the same team. So that's why order does not matter. So in this one you want to say no order, and because there's no order you want your brain just to start thinking about the path it takes. Ask yourself, is there order or not? That's going to be the hard part. Now there would have been 30 permutations, all right, and they've listed them there. Righto, these are the 30 permutations. That means if order was important. If order was important, then an AB looks different to a BA. But since order is not important, then what's going to happen is these 2 are the same. So you go through and you actually realise that you can cut out, okay, a number of them, in this case half of them, and you get yourself 15. Now what you just want to remember is that once you say no order, you're going to be pushing that C. You had 6 friends to play with there, teams of 2 where order doesn't matter. So you want to be just making sure you train your brain to say, which one is it? No order. Pick a C, and then decide how many did I have to play to start with, and how many are in the subset, which is 2 in that case. Now we're up the top of page 167. So here come the examples running down that side. 3 photos are to be selected from 5 photos for use in advertising for a company. How many combinations of these 3 photos are possible? Now again, you might say, well, that's a pretty big clue because you've used that. In tests, we tend not to use the word permutation or combination. We tend to use the word arrangement. How many arrangements can there be? So we don't give you that clue. We'll say how many ways can we take these 3 photos. So all it wants to know is 3 photos. And your job's to say there is no order involved here because we're just deciding that these 3 photos are going to be taken. So it doesn't matter who got picked first, the order is not important. So you know that this is going to involve a C. How many have we got to choose from? There's our 5. How many are in our subset? We only are allowing 3 into the advertising. So it's got a 5C3. And a 5C3 happens to be a 10. All right. So there's the big, he'll just shade them all in and he'll make you realise that there's only 10 different versions. These are all the photos. It's gone and colour-coded it. And we're done. Okay, so that's what we've got. If perhaps you make a mistake and you put order into it, this is the mistake. All right, so I'll just put here, this would not be correct. This would be the mistake. If you did permutations, you did a 5p3, you'd end up with 60. All right, so you can see how much bigger. It's not always double. The other one seemed to be double. This is not double, just depends on the numbers. So this would be the wrong one. Okay. So what we've got, all right, is the next one. Here we go, the string of examples there. 3 students are to be selected from 10 students to form a debating team. Anytime you see the word team, your brain wants to say, it doesn't matter who gets chosen first for the team, all right? So just because I pick Daniel first to be on the team, that doesn't matter because the team is just being made up. So anything that's got team involved means no order. Okay, so just because you got called out first doesn't mean you got given some sort of captaincy or anything like that, because everybody on this team will have the same rank as such. So there is no order. Again, I'll just warn you on, all right, being nice to you, we've put the word combinations there, but in exams you don't tend to see that. So your job is to decide why this is going to be using the C. So again, we've got 10 to pick from, and we're making subsets of 3 students. So we've got a 10C3, which is 120. How many committees of 3 people can be formed from 7? Again, the idea that a committee is just a team of people. Once you're on a committee, once you get chosen, you don't have a rank. Just the first person got called up to be on the committee did not give that person any particular position. All right, so this is just like a team. So again, I'm just putting down the words you want to keep an eye out for, because when it all comes mixed up, you're going to say, where are my sort of triggers? Where are the words that are going to help me? Committee tends to be one. A committee is something that has no order, so it's going to have a C. I've got 7 to pick from, but I'm doing subsets of 3. So a 7C3, which under there says 35. All right, says 35. So again, we've got another one coming up. It says how many groups of 4 books can be selected from a shelf containing 10. So there are 10 books up on the shelf, and I'm going to pick a subset of 4. So whatever gets pulled out first doesn't get given any rank. It's not the best book on there. It's just going to be one of the group I'm taking away on holidays, for example. So this is implying that there is no order. And if there's no order, then it's going to be a C question. There are 10 books to choose from, and I only want to take 4 on holidays. So it's a 10C4, which is 210. And the last couple down the bottom here, all right, have you thinking. We come back to some card questions. We did them last week as well. This is talking about a hand of cards, which means you're going to get dealt 5 cards, is dealt out from a regular pack of 52. In how many different hands are there 4 queens? Now, you might not be a card player, but we're asking you to think about the 4 queens and something else, the 4 queens and something else, the 4 queens and something else. How many are there? That's what it's asking you, all right? How many are there for you to do this? So what we've got here, it says, is this a permutation or a combination? Doesn't matter how the cards came to me. That means when they dealt it to me, did it matter what the first card actually got given to me? Does that give it some sort of rank? It doesn't, just happens to be the first card. So it happens to be a combination. The number of ways to select 4 queens. So it's 4C4. 4C4 means there are 4 queens in the pack, and I want to pick all 4 of them. So do you remember I said that the bottom number can be the same as the top number? It just will never be larger. So a 4C4 is okay. What you'll notice though is a 4C4 gives you 1. All right, the number of ways to select 4 queens is only one way, they're saying. The number of ways to select the other card, to select one more card. So it can be 4 queens and, for example, the 2 of hearts, 4 queens and the 2 of diamonds, 4 queens and the 2 of clubs, and it's going to think about that. But you don't want to sit there and make your brain go and overheat too much. What you want to do is come up with a plan. Now what I tend to do is, I tend to do this. I would have put my 1, 2, 3, 4, and then there's that 5th one there. I want these 4 to be queens. And again, it doesn't mean that it has to be the 1st, the 2nd, the 3rd, the 4th card out. Just by the time the 5 cards got dealt, I got those queens. So there are 4 queens, and I want to pick all 4 of them, multiplied by, now this one here can be any other card. So there's 52 in the pack, and you've already taken 4 of them. So how many are left? There are 48 left, so you're going to put 48 cards left over. So what you want is, out of those 48, you're only picking one more because the total hand is made up of 5 cards. So see that 4 and that 1 at the bottom? That means you've now got 5 cards in your hand. Now it doesn't matter what came out first, it just says order's not important to me. And once you push that in, you'll realise the answer's 48. Now you might have got away with that one because you could sort of see what was going to happen with that easy one. But these card questions will be slightly harder later on. And the bottom example is, this is a multiple choice. Sorry, I forgot he put this in. It's not in the book, but it's just a multiple choice. A special hand of 3 cards is dealt. Now they're only giving you 3 cards from a regular pack. In how many different hands are there exactly? 2 aces. So think about aces. Again, you might not be a card player. There are 4 aces. And you want to pick exactly 2, so that's a 4, C with a 2, because it doesn't matter about the order. Did it come to me first or did it come to me at the end? There's one more card that has to make your hand. How many other cards are there? And there would be 48. All right. Now he hasn't asked you for the answer, he's just asked you for the setting up. So it says 4C2 times 48C1. Here's my hand of 3. And that's from my possible 52 cards. Now the bottom one on page 167 has got the trick, I guess, which is the or. How many groups of 4 or 5 or 6 books can be selected? So before, 2 up, we took out a group of 4, and when we did that we had a 10C4. We were just choosing 4 books for our holiday, and then I'm saying or, so there's going to be a plus, 10C5, that's me picking 5 books for my holiday, or this is me picking 6 books from the shelf for my holiday. So because it says 4 books, or 5 books, or 6 books, I'm adding those numbers. Alright, so once all that comes out, it will give us a total of 672 ways of doing that from the shelf which had 10 books in it. From the shelf that had 10 books. Now we're on page 168, so we're going to get to the bottom of that and then we'll have a bit of a break. More examples. We've got, first of all, a committee. And again, I start getting used to, as soon as I see the word committee, I put no order. So it says a committee of 5 people is going to be chosen from. I've got 7 men and 4 women. The first thing I do is I tend to tell myself how many people that is in total. I've got 7 and 4. I've actually got 11 people in total. Now that usually comes up, so I do it straight away so I don't forget, because the very first question says how many different committees are possible. Now, there's no order because it doesn't matter who got called up first, right? Because once you make your group of 5, they've all got the same standing, I guess. So this is going to be a C. Now, it didn't give me any restrictions. It just said, how many can you make when you've got 11 people? So I've got 11 people, and I'm making subgroups of 5. So it's an 11C5. Now, 11C5 turns out to be a 462. So if I had no restrictions on me, there's 462 ways this could be done. Then it says, what if I give you a condition? How many different committees, same problem, are possible if a particular woman, Diane, must be included? So here are my 5 positions, and again, I'm just giving people another option. You think about placing your restrictions, so Diane has to be on there. Now, she's one of the ladies, doesn't really matter, she's one of the people. So instead of having 11 people to pick from, Diane's already on. So I've only got 10 people, and I need to fill the other 4 in any manner. Male or female, didn't really matter. So it's a 1, because Diane's in, times 10C4. And a 10C4 is 210. So see the 462 committees that were available to us? 210 have Diane on them. Now I'm getting you to start thinking, because if it said what's the probability that Diane is on one of those committees, you would have to figure out how many can Diane be on. That's 210. And the probability you make it over the top answer, which is the no restrictions. Okay, so this is the no restrictions answer. And this is important for when we go to do our probabilities, because this is going to be our denominator. How many ways could this have happened if I didn't have any restrictions on it? So I'm going to call back those sort of words. No restrictions, that's the guy that we need in our denominator. Now there's one more to this problem. It just says how many different committees are possible if 2 particular people must be included. Again, I tend to just use these 5. I put Diane and I put James in. They are already placed. They have to be on the committee. It says so, all right? So that means there were 11 people. I've now only got 9, and I've only got 3 places still to fill. So I think about it like that. That helps me. Whatever helps you, you've now got 84. Again, I'll say 84 out of those 462 have got Diane and James on it. And again, if you were asked a probability, it'd be this number over 462. And that's where we're heading after the break. Amy needs to select a captain and a vice captain and a treasurer, okay? Now, he's just giving you a little bit of a, can you see what's coming? So he really wants you to say, has it got order, or it does have no order? Does it have no order? Order or no order? So first thing is, what do you reckon about this one? Would you say ordered or not ordered? Ordered. So once you say the word ordered, what's the letter, I guess, you're thinking of? You're thinking of the P. Now he's just trying to get you to think like that. Righto. He's got another one coming up. Billy needs to select a team of 8 workers from 100 volunteers. Again, once he's got his 8 people, they're just a team. Nobody in there has any higher ranking than anybody else. So that team suggests order or no order. No order. When you see no order, you're thinking of a C. All right. So again, just getting you to think like that. And this is an example on page 168 down the bottom. So you've got Kai, Daniel, Joe, Dami, Jacqueline and Cara, Tim and Renee are all being considered for a team of 3 people, so I'll highlight that, to represent New Step. Again, I see the word team, I'm thinking order or no order. Teams are no order. And it says how many different teams are possible if all students are available. This is if there are no restrictions. Now this is going to be important if we need to figure out probabilities. So the no restrictions question, all right. So how many people were there? 1, 2, 3, 4, 5, 6, 7, 8. I'm getting 8 people. There are 8 people. Order is not important, and I'm making a team of 3. What would you suggest we put? We've got a C. There's 8 of them to pick, but teams of 3, so it's an 8C3. All right, whatever that answer is. 56. It then says if Tim is ruled out. So think about it. There were 8 people. All right, now I only have, and I'll put here only 7 people. I'm still making teams of 3. I still have no order. So what would you say? 7C3. Did you make that suggestion yourself? 7C3. And again, you can fill those answers in. Daniel must be included. So again, think about it if you want. 1, 2, 3. It says Daniel must be included, so he's in. Now again, it goes back to the original 8 people. Daniel's included, so there's 7 people who can fill the other 2. So I've got 7 people filling the other 2 positions, so that's what I tend to do, like that. And again, the answer is 7C2. But it's about planning it. You want to sort of put your head to work. Jacqueline and Dami must be included. So again, do those 3. Jacqueline is in, Dami is in. So that means out of the 8 people I had, I've got 6 people left over, but they're only vying for 1 position. So I tend to do it that way, which is a 6C1. It says that Renee must be included and Joe is unavailable. So again, 3 along here. So Renee is in, must be included, Joe is unavailable. I had 8, this brings me down to 7, and Joe being unavailable means there are 6 people left to fill the other places. So again, going through, if you want to put it down there, this is a 6C with 2 more positions. And the hardest of the lot is the bottom one. Kara refuses to be in a team with Kai. Okay? Now, you've got to think about what that means. There's two ways to think about it. We could do a shortcut or a bit of a longer version. What you want to do is think. That means Kara refuses to be in a team with Kai. So when the team gets picked, Kara says, I'm happy if I'm on there by myself. So we're going to have to think of how many have just Kara. So I'll put here just Kara plus, again, she doesn't mind if Kai gets on the team and she's not on the team. So just Kara, I better put it Kara, and then I'll have to put the just Kai. And then there's still one other group that we have to think about. What's that one? What was it? Neither of them are on there because, again, Kara's okay if she's not on the team. She just says, I don't want to be on the team if, you know, Kai is on there. So it says, and then there's also the neither are on. Can you think of a shortcut? Anyone want to think of a shortcut? Any thoughts? What's the other group that we haven't considered that they're both on? Now, we don't want that. She says, I don't want to be on there, all right? There is a shortcut, and that is, the shortcut would be, if you've got the total, all right, which we do up the top. Do you remember the no restrictions answer? See the 56? So I'll put the shortcut would have been the 8C3. That was the no restrictions. All right, take away. And you would want to say take away if you've got, let me just put it in a bubble, if you've got Kara and Kai on the team together. Now, how many ways does that happen? So again, you go and figure out for Kara and Kai to be on, that's one, and then there's only one position left with how many people? You would have had 6 people, and they were going for one place. So this will give you the same answer, okay? So this is the shortcut over here, all right? And what does that actual number give us? We better put it down. There's an 8C3, take away a 6C1. 50. All right, now that's the shortcut. Now I think what will pop up in this corner here will be the two versions, all right? So you can see the two versions. I will just rub out that. That was me telling you the shortcut. So what you can see there is exactly what we just thought about. That's the top one, is the just Kara, just Kai, and the neithers, okay, or the shortcut. And I had there that the answer to that is a 50. All right, and that's the bottom of that page. And again, it just says factorial notation is only for permutations, and then I'm about to pause on that one. So that's the top of page 169, all right? So we'll go for a bit of a pause. All right, go for about 5 minutes. Any of my group that want to work on their redemptions, all right, come on down to the pickup. Anybody that wants to work on their redemptions from my group, come on down to the pickup. Jaden, you want it? It's a good one, Jaden. You want it? Joseph, I've also got that redemption, Jackie. What was that? Did you? Well, I had you one. So you remember how you handed me one? Yeah. And the other one would have gone to Dave. So because Dave's on the course, I just haven't got that one. So this is the one you handed me that moment. Yeah. Good one. Nice one. Very nice. Well, what did you do wrong? What did you do wrong? I don't do writing. want yours back? Give us an exercise. So therefore, work on that, because obviously the B lectures play a big part in our final. So we haven't. I'm sure you are, and as I said, there will be two people, but people will count these two more than they want to count others. So that's what I mean. There are people who, even though it's only the tutorial, the only thing that's on next week is the tutorial. Some people, want to turn up, so want to lock in a better. Nobody on Monday can. Robin's there every day. And I'll check with Dad, but I'm pretty sure he's always applied that drop-ins are on until the very day. Any question? school. I know, it's such a small world. It always is. Comes back to that. Alrighty, let's get started. Now this is the probability. Now this is where the brain starts to overheat, I say, because now your job is to turn it into a probability question, or it is a probability question. So what you're about to find is it's about the lead up. I tend to just say if you can build the case just like you did a moment ago, then you won't have trouble with this. So first thing is, how many three-letter arrangements can be made from the word computer? So first thing is, when you're putting these letters, think of it like tiles on a Scrabble game, okay? Even though you don't think if you mix them up it won't make a word, it's not saying that, it's just a three-letter arrangement. So the idea is, do you think there is order or no order involved when you're putting letters down? What do you reckon? Order or no order? Go on, take a guess. Order. Order it is. And if it's ordered, then it's a permutation. So put that down in writing on the top of page 169. When you are looking at letters, all right, letters being arranged makes order, okay, makes order. So you've got to sort of paste that into your head. So because it's got order, then there are 8 letters. So if you need to count them out, there are 8 letters. And we want to make subgroups, I guess, subsets of 3-letter arrangements. So it's an 8p3. Now, the question might have said, what is the probability that one of those arrangements, so how many arrangements were there? There are 336 of them in total. And our job is to say, how many could begin with M? Now, this is where I tend to set myself up. These are my 3 letters. For it to start with M, it gets placed first. Now, there were 8 letters, but the M has already taken its position. How many have I still got left to pick from, to work with? I've got 7. This is a P, so I'm going to put 7p2. You could also have put 7 times 6, because you should find that there are 42 ways, okay, of this happening. So go and check 7p2. I'm going to put my 42 there. All right, so down the bottom here, this is what I've just done. There's 7p2 here. So what I tend to do is say, I reinforce it in my head. You mean that out of the 336 that were possible, 42 of them have the M at the beginning. So what's the probability that yours will start with M? So it's 42 out of 336. Now it's about the setting up. Think about it again. What goes in the denominator is the one where there are no restrictions. So I'll just put that back up there. This is the one with no restrictions, and it becomes your denominator. So I'll put it here. This becomes your denominator. All right, this becomes your denominator. So you think about, right, that's what I'll have to put under there. And then I say to myself, out of those 336 outcomes, how many have M at the beginning? All right? So that's what the probability type of questions are about. Now, there's not a lot of room in here, so try and squeeze it in there somewhere, but here's what it says. 2 students are selected, and it says order not important, so that's pretty handy. Order is not important, so I will be putting up a C there. From a group of 5 girls and 4 boys, first thing I tend to do is say that there are 9 people in total. Now, the very first thing it says is how many different selections are possible. Again, this is the one where there are no restrictions. Just how many can you make if you've got 9 people and nobody gives you any sort of restrictions, okay? Now, I've put down, because as soon as I saw that order was not important, I've put the C, so it's about to circle combination. We have 9, but we're getting 2 people at a time, so it should pop up with a 9C2, which is 36. So there are 36 arrangements, all right, that you can pick 2 students from a group of 9. Now, the harder part of this is how many of these selections have 2 boys. So again, I tend to set myself up. There are the 2 students about to get chosen. Now, because I'm forcing it to say pick a boy out of all of that, then what I've really done is not looked at 9 people in total, but only 4 people in total. Because I'm saying, for me to pick 2 boys, I've taken the girls out of the selection. So they're all gone. There are only 4, and I'm taking 2 boys. So what I need is a 4C2. You mean that out of those 36 arrangements, 6 of them will have 2 boys. So therefore the question at the end says, hence, what's the probability that both of the selected students are boys? What you need, all right, to figure out, and another way, I'll just put it in words, the probability of 2 boys, okay, is the number of ways of getting, and I'll just put BB, which is the top answer of 6, over the number of ways, and I'll put here no restriction. So that would have been the answer 36. So it's about to pop up, but if you need some extra words, what you're looking for is count the ways that you can get 2 boys, which is the 4C2, count the ways when there's no restriction, and then put 1 over the other. Turns out to be a 1 on 6. All right? Next one, again, there's not a lot of room, so see if you can squeeze this in, and I've got a little extra bit to add in there. It's got 5 students are selected. Again, order not important. Same as before, so I'm pretty sure that I'll be using the C from a group of 9 girls and 7 boys. Again, I'm just going to remind myself that's 16 in total. How many different selections are possible containing exactly 2 boys? First thing I'll do is, I tend to just get it out of the road. It didn't seem to ask me, but what I would tend to do is say, what if there were no restrictions? Because I like to see what the biggest number will be. So I've got 11, there's no order, and I'm picking a group of 5. Now 11C5, no, not 11, that was my last answer. So hang on a second, make that a 16. A 16C5. And a 16C5 will give me 4,368. So there are 4,368 ways I could get 5 students from this group of 16 when order's not important. It says how many different selections are possible containing exactly 2 boys. So again, if you want to, you've got your 1, 2, 3, 4, 5. It's got to have 2 boys, and it says exactly. So because it said exactly 2 boys, the others have to be girls. Now, order's not important, so it doesn't matter if it comes out boy, girl, girl, as long as by the end you've got exactly 2 boys and you've got 3 girls. And the only way this can happen, or out of those 4,368 arrangements, this is going to happen in this manner. There are 7 boys and you want only 2 of them for this particular arrangement. There were 9 girls and you want 3 of them. Now remember, these 2 numbers make up the 5. So what you want to make sure of is, have you actually picked 5, which is what you wanted? 5 students are selected. So you'll notice those 2 numbers should give you a 5. So push in a 7C2 times by, and you can push the whole thing in. You don't have to give me each answer. It's just much faster to push. That's my working, by the way. So I'm getting 1,764. Anyone else? 1,764. Out of those 4,368, that's how many will have exactly 2 boys. Now, if they had asked me the probability, I'm just going to add this in there, the probability of exactly 2 boys. So if you could just add that in that line there, a 1764 over a 4368. Okay, because it's asking you to count, and then it should be asking you to find the probability. And whatever that comes out to be, divided by 4368. Anyone else getting a 21 on a 52? A 21 on a 52 simplified. Now again, the last one is the hardest one when they ask you, all right, to come up with, get through that, this page here, the third part of this one says, how many ways can the selection contain at least 2 girls? Now what I tend to do is set myself up. So if the question wants at least 2, the lowest it wants is 2 girls, and if it's got 2 girls it must have 3 boys, and then I'll put the or. What would be the next one up? Because the lowest it wants is 2 girls, so 3 girls and 2 boys, or go up again, so 4 girls and 1 boy. Can I go up again? One more? I'm getting a group of 5, Cassie, I think I can. 5 girls and no boys. So what it actually wants is, it wants me to count out of those 4,368 I think I had on the page before, how many of them will have at least 2 girls. So that's the 2 girl, 3 boy arrangement, 3 girls, 2 boys, 4 girls, 1. Notice it's always got to have 5 people in the group. Now I've got to go through all of those numbers. So what will happen is all of these numbers will appear. The first one is the 2 girls and the 3 boys, plus the next one is the 3 girls and 2 boys, plus there's the 4 girls and 2 boys, 4 girls and 1 boy, and the last one is the 5 girls with 0 boys. In total, 4,032 out of that 4,368. Now again, they could have asked you for the probability. And if they had said the probability of an at least 2 girls in this group, then again you would have taken this number 4032, and I think it was 4368. Just check on me from the page before. Was it a 4368? Alright, and see if that simplifies. So it's about the counting. The counting is the hardest part. The probability is not that hard as long as you know how to count. It's a girl count, so it's a 9C. There it is. So I'll move him out. That's a 4 girl, 1 boy. So it's about planning, because you see, my head doesn't just come out with all of those numbers. My head thinks, well, I'll need to consider the 2 girls, then the 3 girls, then the 4 girls, and then the 5 girls. So I sort of build the case up, and then I write the numbers in. Now the one at the bottom, okay, again it does create, there's a slight degree of difficulty towards the end. So it says, consider the arrangement of the word peanut. Now again, as soon as someone says they want me to arrange letters, do you think there's order or no order? Order, because once there are letters around, there is order. Now order of 6 letters. It says how many possible arrangements are there if there are no restrictions. Now you can either go 6P6, because I'm using all 6 letters, righto, and I'm putting them down, or you could have done the usual 1, 2, 3, 4, 5, 6, and you would have noticed that you would have got your factorial back again. So a 6 times a 5 times a 4 times a 3 times a 2 times a 1. Okay, and a 6 factorial I'm pretty sure was the 720. Alright, so 720 ways. Then it says, what if the word has to begin with an N? So again, just get 1, 2, 3, 4, 5, 6. The N is placed. After that, you've got the other 5 being placed in order. You can either write it 5P5 or you can do a 5 factorial. So it wouldn't really matter what you write as long as you're happy with it. So a 5P5, or you can write a 5 factorial. 5 factorial turned out to be 120. So 120 out of those 720 will start with the letter N. The word begins with an A and ends with a T. So 1, 2, 3, 4, 5, 6. There is an A at the beginning. There is a T at the end. So you've taken 1. You've taken 1. There are 4 in the middle. Again, you can either go a 4P4 or a 4 factorial. 4 factorial should come out to be 24. So 24 of those 720 will have an A at the beginning and it ends with a T. Now I'll just move this little bit of working out so you can read the question. Now there's 2 parts. There's an E immediately precedes an A. I'm going to answer that. And the next one says, or E is just next to A. Now, those 2 questions there, all right, there's something different about them. This one says that E must be placed in front of the A, and it didn't matter where in the word. So I'll go 1, 2, 3, 4, 5, 6. I want the E and the A in that order, but I want it anywhere. So it could place itself in the first and the second position, or it could have been in this E and A sitting there, or it could have been the E there and then the A. So it's going through its little counter. I want the E in front of the A, yep, but it could be anywhere in amongst the letters, but the E has to be next to. Immediately precedes means they're stuck together, they are neighbours, but the E is in front. So what I tend to do is I tend to say this is going to be considered a unit, so this is an E and an A. Now that only happens in one way, but see that box I've put them in? Think of it as a box, think of it as an envelope. It can be in the first position and then there'll be 1, 2, 3, 4 letters after it, or it could have been like letter and then the E and the A and then followed by 3 more like that, or it could have been letter, letter and then the E and the A, letter, letter. So what it's doing is it's saying that box with the E and the A could be placed amongst them, righto, so that's what that diagram is doing. And then the way to figure this out is E and A, there's only one way to place the E followed by the A. Then I count this as 1 unit, 2, 3, 4, 5. So there's 5 factorial or a 5p5 way of placing those 5, when I say units, all right, 4 of them are single letters, and this other unit over here happens to be an E next to an A. So 5 factorial is back to 120. So you'd get 120 of these arrangements. All right. Now the last one that pops up was worded differently. It said that the E is next to the A. So what happens with this one when the E is next to the A? All right. Remember, that seems to say just next to it. It could be the E with the A, but it could have had the A and then the E. So your brain has to say these words are saying it's EA or it's AE. So I'll do the same setup, 1, 2, 3, 4, 5, 6. Here's my unit of 2. There's my EA. But there's actually 2 factorial. There's a 2-way, 2 times 1, because it can either be E times A or A times E. That's the inner unit, if you think of that as the inner unit. And then that unit, so I'll put a dot on it, 1, 2, 3, 4, 5. Again, there's 5 factorial. All right, so that unit could be placed at the front with the 4 letters, or it could be placed in after one of the letters, or placed after 2 of the letters, could be placed at the end. So it's doing all of that in its count. So 2 factorial times 5 factorial gives you an answer of 240 for that one. So that one is 240 there. And the last bit on your page says, what's the probability that the E is next to the A? So again, this is me just figuring out that for the probability that the E is next to the A, I need how many ways that could have happened, which was 240, over what was the number of ways if there had been no restrictions? 720 up the top. So it's a 240 divided by 720. Simplify it and you're there. Righto. What do you come up with? A third. There's a 1 in 3 chance that the E will be next to the A. 240 out of the 720. Here comes our last round. Our last round is all about binomial probability distribution. Now at the beginning you're going to see a lot of reading. So see your page 170 and your page 171. All of that is just setting itself up. So we're about to try and get through that as quickly as possible, and most of page 172. What this is now decided is you're going to get questions where a tree diagram is not practical anymore. And it becomes not practical because you had to repeat it too many times. Now, drawing a tree diagram twice, you know, with 2 things happening, that's pretty okay. 3 is even okay. Once you get past 3, you're starting to get a little crowded in there. So these are going to be situations that you say, this is probably the time I don't want to draw a tree diagram. It's about recognising when do I want to use this binomial. You won't see anyone in the question saying with a big sign waving it, this is the time to use binomial. Your job will be, oh, I've got to try and see the clues in the words. So this is what happens. The binomial probability theory applies to random experiments involving repeated trials, that's one of the things you hear or you look out for, where there are only two possible outcomes. So for example, if you've got a coin, only two things can happen. So if I ask you to toss that coin 10 times, there are 2 to the power of 10 number of outcomes. Do you think you'll draw me a tree diagram? 2 to the power of 10. Can anyone tell me? 2 to the power of 10. How many outcomes are there on your tree? 1024. Are you going to draw me a tree? Don't think so. Not when you've repeated the experiment 10 times. Target shooting. You can either hit or miss. There are two things that can happen. If I get you to trial, pretend you're standing there at a target, you repeat it, say, 7 times, even 2 to the 7 is too large. You don't want to draw yourself a tree diagram. So you get used to hearing these sort of things. When only two things are possible, oh, this is the time I want to be thinking binomial. So you'll hear things are defective and not defective. You'll hear things are cured and not cured, okay? So it's raining or it's not raining. It's a green or it's not a green light, okay? These are the times. Now what you're about to have, what is about to come out here in front of your eyes, as on page 170, is that I've got a guy hitting a target. The probability is 1 on 4. He can either hit the target. His other option is not hit the target. And they're about to do this 5 times. Now straight away, if I asked you to draw me a tree diagram, 2 to the power of 5 is 32. 32 possible outcomes. I don't think I want to draw a tree, but here it goes. This is what Dave would love to put in front of you if you were. All right. Now these are going to have a list of 32 things. There's hits and misses. Now they're the 32 things that could happen. And what you want to realise is, no, we're not going to make you do that, but it's going to show you how it can be simplified. So what he's about to get you to see is a pattern happening. There is one that has all hits at the top, and down the bottom there is one that has all misses. So he's going to get you to see a pattern with these. If you had to go through and count the ones that have 4 hits and 1 miss, there are 4 hits and 1 misses. He's counted them out. He says there are 5 of those. He then goes to the 3 hits, so it gives it a green colour. He looks through the list. There are how many of these 3 hits? He goes through and he finds that there are 5 of these. Now these ones are the 10s. 10 of those green ones. Then he goes and looks for the 2 hits, 3 misses. There are 10 of those. Then he's coming down to 5 of the orange ones. All right, and then he's got that. See the pattern 1, 5, 10, 10, 5, 1? Okay? That's him just saying there's a pattern of it coming out of this. All right? You don't want to draw the tree diagram, but you want to notice a pattern. If you had to figure out that tree, see the one that had the hit? The one that had hit, 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 hit was a quarter to the power of 5. If you were doing the 5 that had 4 hits, see how it's got a quarter to the 4 and a 3/4 to the 1? On that tree, there would have been 5 of those. Then there are 10 of those. Notice how the indices are changing. So the idea is you look at the patterns there. You can see that there's a probability. It's got a 5 on top of it. The next line has got, these ones here have got, see the 4 and the 1 add up to 5. The 3 and the 2 add up to 5. The 2 and the 3, and so on. So there's a pattern involved in that. And even this bottom guy has only got a 5. That's because this one was to the power of 0, as was this one to the power of 0. But we don't tend to put it in, all right? And because there's 5 of them on there, there's 10 of them that are identical, 10 of those that are identical, you end up with these probabilities. Now that comes out the long way. And what you've come to realise is that there's this thing called Pascal's triangle. That's what those numbers were. Now the thing is, you might have come across it in some part of your maths before, or you might be heading towards it. Now you don't have to memorise it because the formula will produce those numbers for you. So again, this is just of interest really. This was if you were expanding your algebra. Now we expanded to the power of 2. Now we don't tend to get you to do the higher powers, but if you had to expand it to the power of 3, you'd get those terms. Now you see all the terms that you're getting. Have a look at the coefficients. So the coefficients is this 1, 5, 10, 10, 5 and a 1. righto, if you had that expansion there. And that's what the Pascal's triangle is doing, okay? It's coming out with those numbers. But again, yes, it's of interest. It's great if we had a lot of time, but we just want to know how to use this because the formula is going to give it to us anyway. Constructing, if you're interested in constructing, the sides have always got ones, and then what you always do is you put your ones down, then you add these, and that's what's going to give you your next batch of numbers. Righto, and then you put ones on the sides, and then you add these. All right, but that'd be great. The problem with that is you've got to have the line before it. So it's a lot of work if you work from that, all right, because you've always got to know the line above it. So instead there's a formula that goes with it. So this is us coming down to about page 171. This is where we want to jump in. Consider an experiment which consists of, first of all, you want to be looking out for repeated trials, and it's only going to have two possible outcomes. Usually they only give you the probability of one thing, and your job is to say the other one must be its complement. So if they tell you one probability, you can find its complement by subtracting it. The idea that P is the probability of what we're going to call a success. The idea of success doesn't mean what you think, like, oh yes, success, it's great, let's have a party. Depends on what the question asks. Whatever the event is that the question is asked, that's usually the successful event, and its complement gets given the failure. So if success is hitting a target, then failure is missing the target. If success is a green light, then its complement is not a green light, which would be considered the failure. So it's important to define your P's and your Q's, because this letter X, this guy here, big capital X, denotes number of successes if you do this n times. Remember, n's the bigger number, right? That's how many times you're going to do the experiment. And the probability of R successes. R should be smaller, but it's allowed to be exactly the same as n. It just can't be more than n. What you notice is there is a coefficient. That's the guy that was coming from the Pascal's triangle. So that NCR, we happened to use it before with the combination. It's got nothing, well, when I say it's got nothing to do with it, for the moment just disconnect it. Don't think of it like a combination. It's just going to give you the coefficient, you know, the 1, 5, 10, 10, 5, 1, whichever row you are in the Pascal's triangle, that gives you the right number. Here's the pattern though. NCR, this is the probability of a success, and the little r is there. Then it goes probability of what we call the complement, and then this group is n minus r. So see the numbers across the top of the indices? There should be an n, then there should be an r, and then there should be the n minus r. So you should be able to see those numbers popping up, all right? Here's the thing. In a binomial setting, there are n independent trials. They're the things that you're going to do over and over again, which have two mutually exclusive outcomes, which you're going to call either a success or a failure. The probability of the success remains fixed. It does not change. It's not like when you eat a chocolate, the next time round you've got one less. Doesn't do that. It's going to have exactly the same probabilities. The probability of its complement stays fixed as well. The random variable x is the total number of successes, and the probability that the event occurs, and it depends on, and again, the biggest number here will be how many times you did the experiment over and over again, okay? And it's going to depend on that formula. You've got this on page 172, so I'm not going to work through it. These are just all of those coming up from there. We're jumping in at the one at the bottom of 172, guys, has already been done, so I'll go through it quickly because we want to do the other four at the very end. Student is taking a true-false test, so there are only two things that can happen, so that's made me think of a binomial. There are 10 questions. That means I'm repeating the experiment 10 times. I don't want a tree diagram because 2 to the power of 10 is a very large number. Assume the student has some knowledge of the subject so that the probability of choosing the correct answer is. They've just given me a probability. So what you notice is you start thinking about what do they consider to be the success, and I guess it makes sense that correct is going to be the success. So what you've got is you've got the formula, which you obviously will put on your resource sheets. It's not like you have to memorise it. N is equal to 10 because that's how many times you've repeated the experiment. Now I tend to set up all my facts. P is 0.8. This is the probability of you getting it correct, which therefore means that its complement, which is Q, has to be 1 minus. So whatever P is, you do 1 minus, all right, and you get its complement. So you now know that that's correct, and this is the probability of it being not correct or otherwise wrong. So you've set everything up, and when the first question gets asked, it wants, what's the probability that the student will answer 9 correct? So see this x equals 9? This is your little r. Once you get the question, right, you want them to have 9 correct. Now that means any 9 could have got the first one wrong and the rest of them right, could have got the second one wrong and the other 9 right. So your job is to say, I don't have to think of it anymore because this will do it all in one calculation. So once you put this number in, you're going to put, most of us would just go straight to this line, 10C9. We will put 0.8 to the 9. Notice the same 9 where it is, 0.2, and you do a 10 minus a 9, which is a 1. Notice the indices up the top, there's a 10, then there's a 9 and a 1. Those two, the 9 and the 1, should add up, all right, to give you a 10 every single time. So that's the first one worked out for you. Answer at least 9. Again, we've got this question of at least. I would say to myself, that is 9 correct or 10 correct. 9's the lowest, and then I can get 10 correct. So then again, you've got all that figured out. So you need 2 of them, and there's your probability. Now our job's to do the last group. So here we go. When tossing a coin 20 times, first of all, a coin seems to have 2 outcomes. So I'm intending to think this is a binomial. What's the probability of getting exactly 5 heads? I'm doing this experiment 20 times, so I'm putting n equals 20. All right, n equals 20. I'm going to set up the probability of the success. Okay, here it is the probability of getting a head. Now the probability of getting a head on this coin is a half, so its complement, which is the probability of, and I'll just put the word not. I know you know what it is, but it's easy just to say it's not a head, so it's also a half. I've got my P and I've got my Q. And the last thing is, because I know I'll have my formula written down, this guy wants me to find exactly 5. So this is the probability when x is equal to 5. There is your R values. In case you're wondering, I'll write the formula, NCR. You've got P to the power of R, Q to the power of N minus R. So here comes the setup. I've got 20 C, and then I've got 5 times by a half to the 5. And what's the Q being put to? 20 take away 5, and you come up with, now I'm not going to push that in, I'm just going to leave it there. You guys can push it in. It's a probability, it should be lower than 1. So I'm doing the setup for all of these. Can you see 20 times one experiment over and over again? You don't want to do a tree diagram. So we're ready for the next one. You can start reading the next one. All right, what is the probability? I'm almost ready to go. If you miss anything, just jump down to the lecture recording to about this part of the recording. All right, I'll put that there. What's the probability that at least 3 heads will occur when a coin is tossed 5 times? I'm repeating the experiment 5 times. I think I'm going to be doing a binomial because a coin has got 2 outcomes. So I think this is saying to me, do a binomial. I've got my n. P is the probability, again, of, it seems to be, of getting that head, which is a half. Sorry, my hand just did that. Wait a minute, we're back again. Where are we? That one. That one. Next one. That one. So this was the probability of getting a head, which is a half, which means its complement, which is the probability of not getting that head, which is a half. And it says at least. So the at least is going to cause the biggest problem here. So what do we want to count? We want to count 3 heads or, 3 heads or Keep writing that down. It's my hand that just triggers that to keep moving. 3 heads or 4 heads or 5 heads. So we want to set all of that up. So I've planned it out. I want the 3, the 4 and the 5. Now I've got the formula written on my resource sheet, so I'm just going to go straight to what my probability will be. So here I go. N is 5, so it's 5C, then I'm doing the 3. It's a half to the 3 with a half to the 2 plus, so that's my 3 heads. Then I'm going for the OR. This is my 4 heads, so I'm going to put a half to the 4, a half to the 1. That's my 4 heads. And then I've got OR, and this is my 5. 5C5, a half to the 5. And a lot of people will say, do I have to put a half to the 0? You don't have to put a half to the 0 because that answer is a 1, but it just makes it easy to check that you've got all the right things. Now again, I won't put the total answer down, but you're just going to practice pushing on your buttons because I really just need to establish the next 2. Here we go on the next one. This is the 3rd one. In a penalty shot in basketball, I score 3 in 4 times. That seems to be giving me some sort of probability of actually getting in the shot. All right. What is the probability that I will miss only 1 in my next 10 penalty shots? Now the thing here is it depends what you call your success. Remember I said before, the success doesn't always have to be get it in. It's more about what the question's asking you. This is asking that I will miss 1 only. So what happens here is it's much easier to say, well, what I'll do is if I know the probability of a miss, and I actually do, because it tells me that he will get it in 3 out of 4, so he will miss 1 out of 4. The complement is not miss, and I know that sounds strange, but it's, you know, the 3/4. You're repeating it 10 times, so you definitely don't want to do a tree diagram. And what you're doing here is making it easy for yourself, because if you go this way, this is the R value and this is the miss. And it's figuring out that you miss only 1. It could be the first one you miss and all the next 9 you get in. Could be the second one you miss and all the others you get in. And the great thing is it will do it automatically. So here we go, 10. C with a 1. Now this is the miss. This is what I've decided is my success because it was the question. So it's a quarter to the 1 and it's 3/4, and then you do a subtraction and you get a 9. Now again, I'm only setting it up. That's the miss. Now you could have done it the other way. Your P and Q could be round the other way. You just have to be careful what you define, because it's important as to what you define as the P, because you'll notice it's important that the quarter got the 1 and that the 3/4 got the 9. All right, so that's what you've got to be very careful of. And there's one more, and we'll set it up. 2 green balls and 5 red balls are in a hat, so it looks like we've got 7 in total. If I select 4 balls with replacement, that means I'm going to do the experiment 4 times, and every time I pick out a colour, I look at it and I put it back in. And the important thing is, because it gets put back in, the probabilities don't change. So the idea is you've got 7 balls all together and you're going to pull out, and there's a chance of it being green, there's a chance of it being red. Now I haven't decided yet what was the success, because I wait for the question, which is what's the probability that at most, I'll work on that bit in a minute, at most 2 of the selections I get a green. Now that's decided what my success will be. The probability that I get a green, all right, green ones, there are 2 out of 7. So the complement, which is not green, will be 5 out of 7. So that's me defining what my success is. I know I've repeated it 4 times. Now here's the thing. At most, I want 2 greens. So if you want at most 2 greens, now what you're doing is going 2 greens, or that had to be the highest number of greens you got. So what's the one lower? 1 green. Or what's the one lower than 1 green? No green. Now it's that planning, that part there, that's the hard part, for you to say What do they want from an at most? So I start at 2 and then I go down. Now I've got to set those three up because there's a lot of adding to do. So here we go. There's a 4, C2, and again, because you've got the P and Q, it's all about what you set up as your success. That's my picking 2 greens. This is me picking 1 green. Oh, go back. 1 green. Almost time. It really just wants me to say goodbye to you, I think. And then this is the no green. And as I said, I tend to put that in, even though, it's got a 0 there. I just always keep an eye that the 2 top indices are always adding up to a 4. And again, I'll just put equals because that's the hardest part, setting that up. All right? So when you've got time, push them all in, put the numbers in, and then in the tutor, I'll just tell Dave if you want to check the answers to all of those. All right? But go and push them all in. And as you can see, the very last one says, congrats and good luck because you have made it to the end of 125. We've still got a tutorial, though, next week. We have no more lectures. All right? So some of you I don't get to see unless you go to the drop-ins. Make sure you start thinking about your summaries. There'll be a little practice paper, a revision paper, as usual, because you've done this before. Check where your exams are, all right? Make sure you know the room. See you at drop-ins for a while, okay? Daniel, it's been a pleasure having you here. It's been a pleasure. That's it. Well, that was a pleasure. Because then I knew I wouldn't go wrong because you'd tell me. See if my daughter's out there. She should be waiting for me, all right? You might run into her. Yeah, she should be. She needs a lift. ICT, that's the one. ICT is the one on top of the car park, isn't it? Yeah. Well, it depends where you come, though. What time is it? Pleasure, and see you around somewhere else, around the campus.